So you need to learn to do polar integration so we don't have to do trig sub ever again. Well, almost ever again.
Most of the time.
Most of the time, probably, maybe. I don't know. It might save us trig sub once.
That's good enough.
It'll definitely save you trig sub at least 50 or 60 times over the course of the semester. And knowing how bad trig sub is, once is worth it, right? So our goal is going to be to write D area, right? In terms of R's and thetas, right? You guys with me? Okay, so the first thing I'm going to do is I'm going to draw a plane, and I'm not going to label anything. Okay? Plane, right? So you have normal coordinate axes. I don't actually care what these are, which is why I'm not labeling them. So these could be the y and z axis. It might be a good idea to convert to polar in the yz direction instead of the xy direction. You guys cool with that? Okay. Trust me, the conversions work the usual way. I want to think about a D area. And when I'm thinking about D area, really I'm looking at delta area, right? I think that's where I got those things from. I thought there's some surface, and I chunked it up into little bits in the x direction and little bits in the y direction. And I said, okay, over here's a delta x, and over here's a delta y. And so a delta area is a delta x times a delta y, right? And then we took a limit, and we got D area equals dx dy. That's all with me on that? Okay, same thing, except I'm going to think about a little change in the radius and a little change in the angle. Cool? So, and I'm not going to draw too much of this. I would draw a whole mess of circles, right? Just a little bit offset from one another. I'll draw that over here. I know you guys aren't impressed by that, but that takes forever to learn how to do.
No, I've tried. I'm kind of impressed.
Okay, and then, so these are change in, right? These are all like delta R wide. You guys see that? And then there's, what's a change in angle look like? So like, there's an angle, right? 0 maybe. Here's another angle. Here's another angle, and another angle, and another angle, and another angle. You guys see this? So we're chunking this whole thing up by little change in angles. And I'm writing these out here, but really these are the angle in the middle that's changing, right? You guys see that? Okay, so I'm going to draw just one of those little segments out here. And I'm dumping that. You guys see this? So there's one of the rays. So this little angle in here is delta theta as an angle. You guys all good with that? And then someplace out here, there's one of those circles and then the next one of those circles. So I'm going to do circle, next circle. You guys all with me on this? So this thing is almost a little square, right? Well, not really. It's almost a little rectangle, right? It's a little bent, but it's basically a rectangle. So its area is basically its width times its height, right?
As changing theta approaches 0, it approaches a rectangle.
Yeah. You guys all see that? Like as I crank down on theta and r, this thing's actually going to become a rectangle, right? I just need to know how big the suckers are. And they're not uniform, right? Like, these ones in here are way littler than these ones out here. In the limit, they'll all be tiny anyway. But I need some formula for this, right? I need to know what, like, I'm thinking this area here is change in area, right? But I need to know what that is. So how wide is this thing? Yeah, it's like delta ry. Okay, so far I'm thinking delta area is about delta r times
Delta theta in radians.
ooh. But why is this one in here smaller than that one out there? What's the difference?
Smaller radius.
Yeah, the radius, right? It's gone out further because there's a formula for arc length, right?
So S equals R theta.
S equals r theta, right? So what's the radius here? Yeah, it's whatever the radius in that little chunk is, right? So there's an r, and then this side is r delta theta long. You guys see that?
There's no symbol for long.
I don't even know what that means. Really.
He's joking.
R delta theta long, like, is that, why would that be the long one if it's,
Oh, sorry, I just meant in length, this thing is r delta theta.
oh.
Right? The measurement of this is r times delta
He
theta.
took it really literal.
Sorry. So my change in area is about delta r times
R delta theta.
r times delta theta. And of course that's inconvenient. So I'm going to rewrite that as change in area is about r delta theta. And then as I take the limit, what's the area going to be? But as I limit the change in r and the change in theta going to 0, I'm going to get the instantaneous change in area is r. Where's that r coming from? Yeah, that's this radius, right? D
DRD theta.
dr d theta. So the point of converting to polar is this. This is the only thing you need other than the usual conversion formulas. You guys remember the usual conversion formulas? Yes? Okay. You want to do our horrible example from earlier?
Yeah.
Okay.
So earlier we were trying to integrate over the open or the closed unit disk x squared plus y squared d area, right? You guys with me on this? Okay, so I'm going to convert this to polar because I tried it in rectangular and it sucked, right? So what's d area in polar? R dr d theta. This thing, this r, is part of the d area. You guys with me on that? Do not lose that thing, you need it. That's what's accounting for the fact that you swap to polar. Now, you also have to swap the function to polar. So what's x squared plus y squared when you convert to polar? Sorry, it's r squared.
Yes.
It's not 1, right? Because I'm not limited to just the unit circle, right? I'm inside the unit disk. Which brings up, where do the r's live? The highest they can be is 1.
Right.
Lowest is 0.
And the lowest they can be is 0.
Yeah.
And where do the thetas live in the unit circle? From 0 to 2 pi. What does this look like I'm integrating over? No, dumber. Think dumber, right? What does it look like I'm integrating over? Like, if you ignore that shit, what do these limits look like?
Circle.
Those look like a rectangle, right?
Oh.
So you need those so you know it.
You guys see that? Disks are polar rectangles. You guys see that? Which makes your life easier. Right? Anytime you're integrating over some some junk that's in between a couple circles and a couple angles, that's a polar rectangle. If you convert to polar, this will be dead easy. If you keep it in rectangular, it'll be a disaster. So,
With the r dr d theta,
yep.
what does the r on the left mean? Like, does that become multiplied to the r squared?
Yeah.
Okay.
This guy has to get incorporated into your function before you integrate. And what it's doing is it's compensating for the fact that you're adding up polar areas now instead of rectangular areas. Because rectangular areas don't care where the hell you are, right? A delta x by delta y is the same size everywhere. But a delta r times a delta theta changes depending on the radius. You guys see that? So it's compensating here. So you get here the integral of 0 to 2 pi. Oh, we can use the trick. No? Okay. Integral from 0 to 1 of r cubed dr d theta, right? You guys see that? Now, you can use the double integral trick here.
You get 0 to 2 pi of 1 d theta, and you get times 0 to 1 of r cubed dr.
Good. You guys see that? Right? This is just a function of r cubed. So this whole thing, right, the r stuff can get factored out, and then you're integrating 1. So you're going to get a 2 pi times
0. Wait, no, that times.
No?
1/4 r.
Okay, you get the integral from 0 to 2 pi of 1 d theta times the integral from 0 to 1 of r cubed dr. You guys buying that?
Yep.
Oh. So it just becomes 2 pi.
So I get 2 pi times
R cubed over, or r to the 4th over 4, integrated from 0 to 1.
Just 4.
Which, yeah.
Okay, I forgot to integrate in the first place.
And man, there's nothing more comforting than getting pi over 2 at the end of a problem. Right? Because you know you're right when it comes out to pi over 2. You guys cool with that?
Yeah.
What is the interpretation of this? I think you guys know what the shape is even. What was the shape I started with at the beginning?
Paraboloid. I mean,
Yeah, that's a circular paraboloid, right? And I said the area underneath the circular paraboloid over the unit disk, right?
Oh, it's a cup.
So this is a cup,
Well, kind of. It's flat on the bottom. Like,
right? There's a cylinder,
yeah.
and out of that cylinder we've taken the circular paraboloid.
Yeah. Like it's a really flat cup. It's like a shot glass of some sort.
Yeah, it's a funky little shot glass. There's one in the math lab. I should have brought it.
and where did that 1/4 come
The 1/4 came from
The actual.
this guy here, this integral from 0 to 1 of r cubed dr.
Oh.
That comes out as r to the 4th over 4 evaluated from 0 to 1.
I think we figured it out.
You guys cool with this?
Mm-hmm.
Okay, so what does converting to polar save you?
Lots of times.
Shitloads of time.
It just saves you period when you're working with rectangles. I guess.
Yeah, so when is it a good idea to convert to polar?
Whenever you're dealing with a disk.
Yeah, when you're doing things with circles. When is it a bad idea to convert to polar?
Rectangles.
When you're dealing with stuff that aren't circles, right? You guys see that? What if you're dealing with a line and a circle?
Probably still.
So like what if your region D looks like
Probably still. Wait. Still polar. Yeah, still polar.
I'd probably convert to polar myself. You guys cool with that? It's gonna be annoying either way.
Yeah.
Cool? Problems like this happen. Maybe I should have drawn this thing upside down.
Oh,
Does that screw with your guys' brain? No?
I'm fine with that.
I've seen it.
Figure out what this is.
What's the,
Yeah, anytime you're putting water in a cylindrical tank or in a pipe,
oh, no.
right? Problems like this come up all the time.
Ouch.
Especially these wastewater engineering people have formulas written down and that they have tacked over their desk for stuff like this because they don't want to do the math every time and they have to do this a lot.
Surprised they don't carry it
Cool.
around like a freaking Bible.
Yeah, they do. Tacked to the desk, picture on the phone. Got it? Cool. Questions on this? So the only thing you need to remember, right, is don't forget the R when you change. And don't forget your usual conversion formulas, which I haven't written down at all. But I trust that you guys remember. Is that a bad idea to trust that you remember?
It's in the back of our book, I'm pretty sure.
Okay, so what are the rest of the conversion formulas? X is R cosine theta, and Y is R sine theta. And what should you keep in mind?
X squared. R squared.
Yeah, so either cosine squared plus sine squared is 1, right? Or x squared plus y squared is r squared. Either one, but remember one of those then. Cool? Okay, deal. Oh, actually, also, what the? How can you figure out what the volume inside the parabola is? Now that we know that the outside is pi over 2.
Cylinder, so you can just
I get the area of the cylinder and then subtract, right? Cool. Okay. Or you could go back and integrate over d1 minus that thing.
We're going to get pi over 2 again, aren't we?
You guys see that?
Oh, wait.
Yeah?
Okay.
You get pi over 2 again out of that piece. And then out of this piece, you'll get the volume of the cylinder. Right, which will be the area of the base times the height of 1. I cheated just a little bit.
3/4?
I happen to know that this was 1 high.
No, no. 3/2.
How would you figure it out if you didn't know? Yeah, you'd want to take this x squared plus y squared and evaluate on the edge, right? But x squared plus y squared is 1 when the radius is 1. Cool?
So
Okay.
would it be 3/2 pi?
I have no idea.
This is be pi over 2.
It'd be pi over 2 again. Right? Because the area of a cylinder, or the volume of a cylinder, is the area of the base times the height. Height's 1. The area of the base is pi times r squared. So, this is pi over 2 too? This is pi minus pi over 2? Oh, that's cool. That's a way to cut a cylinder in half that's fun.